Just now we finished a few of the library blocks which we use in a source and sink. Okay, now we will learn about some discontinuity library blocks. Few of the blocks I have taken here which we use most frequently in our simulation and modeling. Okay, so here one is backslash. So the backlash block implements a system in which a change in input causes an equal changes in output as well, except when the input changes direction. When the input changes the direction, the initial changes in input has no effect on the output. The amount of side-to-side play in the system is referred to as a dead band. The dead band is centered about the output. In this figure, you can see here in initial value, we have suppose minus 5 to 5. In this band, whatever the output will become a zero, dead. Output will not be used here. So there are a few modes as well, mode like disengaged, engaged positive direction, engaged negative direction. So inside that, this is a disengaged mode. Inside that, in that range, it is like inside this dead zone will be occur, or in output this remains as a constant. If you want zero, anything we want point of that, we can select that constant as well. Okay, in a positive and means it will be going to increase, then it will become a zero. In that only it would happen. When it's negative, then when it is going less than zero, then it will become a like dead logic. In that way, we can refer. So in that backslash, where we when we can take this block backslash, you can see here more model backlash where the dead band width specific the amount of play in the system is written. So there are some parameters we can give. So what is our dead width? Our dead width is specially known as like what we are giving there, the dead width here. You can see here the initial input that we can define in an initial dead zone. Like in a table, it's shown like we have some initial condition. Then dead width, if my dead width is 2, so it will take like what is that width here you can see this is the width minus 5 to 5, so this width is complete 1. In that way it will work. So in that scenario the width is like input plus 1 input minus 1. In that way it will work. So initial condition is 0, it's given here. So if I am changing initial condition, then it will also change. So I have created here some logic here. Now we can see once I have simulated this model. First, the one repeating sequence I have connected here from minus 4 to 5. So what is going to happen with this, you can see in this video. What happened, the backslash in this repeating sequence, that it is started after this first input and it is deleted that one. It is deleted that one. It is not that first one, how it is working, whatever the values in between that it is going to be deleted. One value here. Okay, but here you can see in this sine wave graph easily in good manner, where we have like bound whatever a part of this plus 5 to minus 5. That value should be work. A part of this, our complete logic will become a dead. So here you can see the sine wave which I have created from 1 to minus 1, and like 1 to minus 1 in that way. It's like it will go to 0 to 1, then again 0, then minus 1 in that way. But here you can see it works only till minus 5. Then logic is dead. Again that it is started, then again the logic is dead. In that way. So this is the main use of dead logic. Okay. So in the next we will see that dead zone. Dead zone is referred for what? Everyone will get this kind of questions. Okay. So give me a second. I'm showing you here. You can see the dead zone block generates the zero output within a specific region called it is dead zone. You specify the lower limit LL and upper limit UL of the dead zone as the start of dead zone and end of dead zone parameters. The block output depends upon the input U and the values of lower limit and upper limit as well. Okay, so where the input is like greater than equal to a lower limits, and it's less than equal to lower limits, then the that time being output is 0. And if upper limit is greater than whatever the input is greater than the upper limit, then that input minus upper limit will be happen. If my input is less than the lower limit, then input minus lower limit will be happen. So one basic example, few of the basic examples I have created here. One which is like same repeating sequence which I have given, and I have given here range -2 to 2. So you can see here in a simple way, this logic will work only in -2 to 2. Even my input is -4 to 5, but it's worked here till only -2 to 2. Whatever above or below this, it's considered as a dead zone. These values are converted in this bonding and frenching. In this sine wave example, I think you will understand better in dead zone. I have connected two inputs of the sine wave and all in that way. So here you can see I'll be also having a sine wave, but my sine wave is working with the 0.5 only due to that dead zone logic. Here you can see at dead zone I have a limit like start zone, and end zone I have -0.25. If I am going to change this -1 to 1, if again I am simulating this model, okay, so now what is going to happen with this? This may be curious question, okay. So here both things are equal, nothing will be present, okay. That's why that logic is deleted and it's become one single line. So that's working principle of dead zone.